So we are into the unit 4 and starting with unit 4, the concepts involved in this unit are measure spaces, measurable functions, integration, signed measures, and most important Radon-Nikodym theorem, measure and outer measure and measurability, the extension theorem, and finally the product measures. So looking into the first definition of the unit, and it is about what do you mean by a measurable space. So definition, by a measurable space we mean a couple, say x, b, consisting of a set x and a sigma algebra b of subsets of x. So by a measurable space we mean a couple x, b, where x is a set and b is a sigma algebra of subsets of x. So that is what I mean by a measurable space. And a subset A of x is called measurable if A is in B. So a subset A of x is said to be measurable if A belongs to the sigma algebra. Now after knowing what do you mean by a measurable space, let me recall what do you mean by a measure, what we have defined. So if a measure to be of outer measure, then measure is a mapping from M, which is a mapping from M, which is a collection of measurable sets, to R union infinity. So we have M to be such a mapping. Then the M satisfies these three properties, where M is a non-negative extended real valued set function, where a set function by we mean domain of definition is a class of sets, and a measure of empty set to be 0, and finally if we have EI to be a sequence of disjoint measurable sets, then we have a measure of union of EIs to be same as summation of measure of EIs. So this is what we meant by a measure. So just try to recall it. Then we have a definition of measure on a measurable space now. So the definition by a measure on a measurable space xb, we mean a non-negative set function defined for all sets in B. That is, if mu is a mapping from B to R union infinity, satisfying these two properties. So mu of empty set should be 0, and mu of union of EIs to be same as summation of mu of EIs, where each EIs are measurable and EIs are disjoint. So by a measure on a measurable space, we mean a non-negative set function satisfying these two properties. And second property is often referred to as countably additive, and also mu is finitely additive. So this is what we mean a measure on a measurable space. So having learnt what do we mean by a measurable space and what do we mean by a measure on a measurable space, now we are capable to define what we mean by a measure space. So measurable space, measure, and a measure space. So by a measure space, we mean a measurable space xb together with a measure mu defined on B. So by a measurable space, we mean a measure space xb together with a measure mu defined on B. So the triplet xb mu is said to be a measure space now. So this is what are the concepts of a measurable space, a measure, and measure space. Now we are into some examples pertaining to measure space. So for the first we have RMM to be a measure space, where R is the set of real numbers, M is the collection of measurable sets, and M is the Lebesgue measure. So having R to be real numbers, set of real numbers, M to be the collection of measurable sets, and M to be the Lebesgue measure, I have that to be a measure space. On a similar note, I have RBM to be a measure space, again where R is a set of real numbers, B is the class of Borel sets, and M is again Lebesgue measure. So finally we have an example. I am taking X to be an uncountable set and B to be the set of all subsets of X which are either countable or complement of a countable set. Then B is a sigma algebra, and we define a measure on it by setting mu of A equal to 0 for each countable set and mu of b equal to 1 for each for each set whose complement is countable. So what we are trying to do here is we need to construct a measure space. So to construct a measure space, I need a set X, a sigma algebra B, and a measure mu. So here X, B, mu are, X is an uncountable set and I am having a sigma algebra B where the collection is defined as follows. It is set of all A subsets of X, either A or A complement is countable. So I have got X and B now. And to define a measure mu, I am defining it to be 0 for each countable set and I am defining it to be 1 for each set whose complement is countable. So I need to prove that to say this as a measure space, have X which is uncountable set and I need B which is a sigma algebra, what I have defined like this, and if I need to prove that to be measure space, I need this to be sigma algebra. So the thing is, if I have an uncountable set now, say X, I need to prove this as a sigma algebra, and what I have defined mu as a measure, I need to prove that as a measure. So for the first, here we will prove this collection B as a sigma algebra, and in the next what we have defined as a mu, for that we will prove that as a measure. So that proving this as sigma algebra and this as measure implies that X, B, mu is a measure space. So we have B to be the collection of all subsets of X A, either A is countable or its complement is countable. For the first, I have empty set to be in B as empty set is countable. And the next, if I need to prove to prove B is a sigma algebra, I need to prove if I take an element in the collection, its complement is in collection and it is closed under countable union. So I need to prove its complement is in the collection and countable union is in the collection. For the first, if A is in B, then A complement belongs to B, because clearly if A is countable, then A complement will be in the set, or A complement is countable, then A in will be the set. That is the definition of this collection, as B is either A is countable or its complement is countable. So clearly if A is in B, then A complement is in B. Next, if I take a countable sequence of sets in B to prove this, like the countable union is in the collection, I am taking a countable sequence of sets in B. For each AI to be countable, then A is union of AIs, and knowing the fact that countable union of countable sets is countable, we are done. If not, suppose not all AIs are countable, if not all sets are countable, then there exists at least one index, say J, such that AJ complement is countable, because we need that either A or A complement is countable by the definition of B. If not all AIs are countable, I have at least one J, AJ complement is to be countable. Then A complement is contained in AJ complement, which implies that A complement is countable, so that its complement will be in the collection, which implies that B is a sigma algebra. Now we have an uncountable set X, and we have defined a collection B, and we have proved that as a sigma algebra, and we have also defined a measure mu of A equal to 0 if each countable set, for each countable set A, and mu of B equal to 1 for each set whose complement is countable. I am just remaining to prove that mu is measure, so that we will end up with X B mu to be a measure space. Now we are left to prove that mu is a measure. What we have defined mu of E to be 0 if it is countable, and 1 if its complement is countable. So if I need to prove mu as a measure, I need to prove two things. One, the measure of an empty set is 0, and it is countably additive. So clearly measure of empty set is 0, as empty set is a countable set, then we have defined it to be 0. So we have 0, and to prove that if mu is countably additive, I will consider a sequence of disjoint sets in B, and I will put A to be union of AIs. My claim is to prove that mu is countably additive. So we have two cases here where each AIs are countable, and in the other case not all AIs are countable. So in the case one where each AI is countable, we have A to B union of countable sets. So countable union of countable sets is countable, though, so we are done. So as union countable measure of countable sets is 0, we have a union to be 0, which is same as the summation of mu of AI. So in the first case we are through. In this next case, suppose not all AIs are countable, then there exists exactly one AJ such that AJ complement is countable. Exactly one AJ, because if there are two sets of AJ and AM such that AJ complement and AM complement are countable, then by De Morgan's law we have the complement of their sets, union of complements of sets to be AJ complement intersection AM whole complement, which is an complement of empty set, which is the whole of the set X, which we get to be countable, which is a contradiction to the fact that X is uncountable set here, so that there cannot be two sets such that their complement is countable. So we have exactly one AJ such that AJ complement is countable. So which implies its complement is countable means we have the measure of the set to be 1, so measure of A will be 1, which is same as the summation of measure of those sets. So this proves both the cases, so that mu is a measure. So we have a set X and we have proved B to be sigma algebra, and now we have arrived at mu to be measure, so that X B mu is a measure space. We have three propositions to follow. If X B mu to be a measure space, then we have, if A and B are two sets in the collection such that A is subset of B, then we have mu of A to be less than or equal to mu of B, which we have seen as a monotonicity property for a normal measure. And again for the next we have, if we have EI in the collection, then mu of union of EIs is less than or equal to summation of mu of EIs. Again, what we have seen as the countable subadditivity of a measure, we have mu to be countably subadditive. For the next and the final thing, we have, if for EI in the collection and mu of E1 to be finite, the measure of E1 to be finite, and EI contains EI plus 1, then mu of countable intersection of EI is same as limit of mu of ENs. Again, we have saw this in the theorems as in that of in a normal measure what we have defined, and the proof of all these three things follows as that of what we have proved for a normal measure, and it is again left to you to prove these things. Next we have some set of definitions. A measure mu is called finite if the measure of the set is finite. So a measure mu is called finite if the measure of that set is finite. A measure mu is called sigma finite if there exists a sequence of sets in B such that that set can be expressed as the countable union of the sequence of sets, and measure of each such set is finite. So a measure mu is called sigma finite if there is a sequence of sets in the collection such that that set can be expressed as the countable union of those sets in the sequence, and the measure of each such set should be finite. For example, if you consider the interval 0, 1, the Lebesgue measure on that interval 0, 1 is finite. So this can be example for a measure which is finite. So 0, 1, the Lebesgue measure what we have defined on this interval is finite. If you consider the Lebesgue measure on R, it is sigma finite because R can be expressed as the countable union of the sets minus n, and where measure of the set minus n is 2n, and this is clearly finite. So I am able to express R as the countable union of the sets, and the measure of that set is 2n, which is finite, so that the Lebesgue measure on R is sigma finite. But remember that the Lebesgue measure on R is not finite. The Lebesgue measure on R is just sigma finite, but Lebesgue measure on R is not finite. So coming to the next set of definitions, as that of we see for a measure to be finite and sigma finite, we have for a set to be finite and sigma finite. So let X be mu be a measure space. A set E in the collection is said to be of finite measure if measure of that set is finite, and a set E is said to be of sigma finite measure if it is a union of countable collection of measurable sets of finite measure, same as that of what we saw here. A set E is said to be of sigma finite measure if it is a union of countable collection of measurable sets of finite measure. So this is the definitions regarding finiteness and sigma finiteness. Let me see some remarks regarding this. We have two remarks regarding sigma finite measure, and for the first, every measurable subset of a set of sigma finite measure is itself of sigma finite measure. So a measurable subset of a set of sigma finite measure is itself of sigma finite measure. To see the proof, let E be a set of sigma finite measure. Now I have E to be a set of sigma finite measure, and I will have a subset, say E1 of E, which is measurable. E1 is measurable. Now I need to prove E1 is of sigma finite measure. Since E is of sigma finite measure, I can express E as the countable union of some sets where the measure of those sets will be finite. So given that E is of sigma finite measure, I have expressed it as a countable union of some sets where the measure of those sets is finite. Now if I consider E1, this is nothing but E intersection E1. Having expressed E as a countable union, I will replace E by countable union of xn's intersection E1. So again, this is same as union of xn's intersection E1 n from 1 to infinity. So I have expressed now E1 as a countable union of this set, where again if you take union of measure of this set, measure of xn intersection E1, this is less than or equal to measure of xn, and having measure of xn's to be finite. Now I am able to express E1 as a countable union of some set with the measure of that set to be finite. So that implies that E1 is also of sigma finite measure. So having E to be sigma finite measure and E1 to be subset of that sigma finite measure, we have that set to be also of sigma finite measure. Next, coming into the next, the union of countable collection of sets of sigma finite measure is of sigma finite measure. So union of countable collections of sigma finite measures is of sigma finite measures. Now I consider EI to be the sequence of sets of sigma finite measure. So I consider EI to be the sequence of sets of sigma finite measure. I need union of countable collections of sigma finite measure to prove that. So if I consider union of EI's now, since EI's are 6 sets of sigma finite measures, first of all, EI's are unions of x and I, say, because the index with respect to each EI, so I have x and I, where n running from 1 to infinity, along with measure of x and I to be finite. So given that EI sequence of sigma finite measure, considering I have EI to be the union of some sets with measure of that set to be finite. So now if I need union of countable collections of those sets, I will consider union of EI's, which is nothing but union of these sets And since now I have expressed union of EIs as union of some sets, where union of countable collections of sets, where again the measure of these sets to be finite, clearly the countable union of countable collections of sigma finite measure is of sigma finite measure. Next we have a definition regarding mu to be of a semi-finite measure. So we will say when a measure is said to be semi-finite, see that if x be mu to be a measure space, then mu is said to be semi-finite if each measurable set of infinite measure contains a measurable set of arbitrary large finite measure. So see that mu is said to be semi-finite if each measurable set of infinite measure contains a measurable set of arbitrary large finite measure. So this is what we have semi-finiteness. So note that the notion of semi-finite is weaker than the notion of sigma finiteness.